Following on from the previous two videos, we got to this stage here where with four strips, the area underneath the graph between A and B is given by this. It's given by this. So with four strips, it would be from k equals 1 to 4. So now to increase our accuracy, we would increase the number of strips. So in this case, let's increase it to 8 strips. So you would get B, take away A, which would then give you this length, cut up into 8 equal pieces. So delta x here represents delta x here is this, okay? And then so with 8 strips here, the area underneath the function here is approximately this. Okay, so you can actually, this here is a constant, you can take it out. So the area is approximately this. So with 8 strips, the accuracy increases. So now let's do it for a general case for n strips. So with n strips here, then the area underneath the function here between A and B is approximately this thing here. Okay, but then so at the moment the area is approximately this. But then to get the true area, then you would take the limit as n tends to infinity, meaning that at the moment we've got this many strips here. But then if you make n to be, let's say you have 1,000 strips, then it becomes more accurate. But then if you have 10,000 strips, then it becomes even more accurate. If you have I don't know, a billion strips, then it becomes more and more accurate. So the point here is that the area is currently approximately this. But then when you take the limit as n tends to infinity here, meaning you have an infinite number of strips here, then we can say the true area equals this when you start to take the limit of the whole thing. Okay, so at the moment the area is approximately this. But then as you when you take the limit, then when you take the limit as n tends to infinity, then you can say the true area equals this whole thing here. When you take the limit, then you can say it equals. But before the limit, then you can only say it's approximately this. And here's what's going on here. Let's just imagine that the area here. Happens to be pi. Okay. So remember the concept behind limits. If you want, let's say if you want the true area of this, correct to let's say 3 decimal places, then I know that I can get to within 3 decimal places by increasing the number of strips. Let's say that the area of this thing here is pi. Okay, let's just pretend it's pi. Let's say you want it to 7 decimal places. Correct. Let's say you want the area correct to 7 decimal places. Then I know, I am 100% sure that I can get to within your degree of accuracy by increasing the number of strips. Let's say the area here is, let's say the true area here is pi, and then you happen to want the true area, you happen to want it correct to let's say 100 decimal places. But then I know that I am 100% sure that I can get to within your specified degree of accuracy by just increasing the number of strips. I know that I am 100% sure that I can get to within your specified level of accuracy. Let's say you want it to 1,000 or 10,000 decimal places. I know 100% sure that I can get to within this level of accuracy by increasing the number of strips. The point is that, remember the idea behind limits is that no matter what degree of accuracy you want it, I am 100% sure that I can get to within this level of accuracy by just increasing the number of strips. So because I am because I am always 100% sure that I can get to whatever accuracy you want. Well, because I know that I can get to within whatever accuracy that you specify, we can say that, oh, the area equals the limit of this. Because remember, the concept of limits is that no matter what degree of accuracy you want it, if I can get to within that level of accuracy, then we can say, we might as well say that the true area equals this thing here when we start to take the limit. Okay, I hope you understand. It's important to understand the concept behind limits. If you don't understand the concept behind it, then scroll back to one of the earlier sections. Okay.